Hi there, this is Stu Schwartz from MasterMathMentor.com. This is video AB04, and the topic is limits from a graphical point of view. It covers the AB manual pages 15 through 17. Let's examine the graph of f of x equals x cubed minus 8 divided by x minus 2. To the right, you see a table of values for x when x is close to 2 and the corresponding values of f of x taken out to 4 decimal places. Note that when x equals 2, there's an error because we're dividing by 0. Note that we show this with a hole in the graph. It should be obvious that as x gets closer and closer to 2, the value of f of x becomes closer and closer to 12. Now, f of x never actually equals 12, it just gets close to it. This is the essence of the concept of a limit. We say the limit of f of x as x approaches 2 equals 12. The notation we use to express this is shown on the screen. We say the limit of f of x as x approaches 2 equals 12, or the limit of x cubed minus 8 divided by x minus 2 as x approaches 2 equals 12. The informal definition of a limit answers the question, what happens to y as x gets close to a certain value? In order for a limit to exist, we must be approaching the same y values as x approaches some number c from either the left or right side of c. If this does not occur, we say that the limit does not exist, we write d and e, as we approach c. This sounds complicated. We can make it clearer with a humorous example. Suppose you are robbing a bank late at night. Between the tiles on the floor, the bank managers have installed a wire. And this wire, when tripped, will sound an alarm. Let's say that the variable x represents our position along the tiles. We can say that as x approaches the crack from the left-hand side, or if we want to, the negative side, the closer we get to the alarm going off. We are safe anywhere to the left of the crack. However, the closer we get to the crack on the left-hand side, the closer we get to the alarm going off. So we could say that the limit as x approaches the crack from the left or the negative side is the alarm going off. The same thing is true if we approach the crack from the right-hand side. We could say that the limit as x approaches the crack from the right-hand side, or the positive side, of our steps is also equal to the alarm going off. So the direction really doesn't matter. It makes no difference whether we approach the crack from the left-hand side or we approach the crack from the right-hand side. Our limit will be the alarm going off. So we can state that the limit as x approaches the crack of our steps is the alarm. Suppose the bank managers installed a transparent wall just to the right of the crack. as we approach the crack from the right-hand side, we do no longer approach the alarm going off. The worst thing that might happen to us is getting a bloody nose, but we do not approach the alarm going off. So we could state that the limit of our steps as we approach the crack from the right-hand side is a bloody nose. So if we approach the crack from the left-hand side, the limit is the alarm going off. But if we approach it from the right-hand side, the limit is getting a bloody nose. So direction now matters. So we would state that the limit of our steps as x approaches the crack does not exist because the left-hand limit does not equal the right-hand limit. We show the notation for the left-hand limit, the limit of f of x as x approaches c from the left-hand side, and the right-hand limit, the limit of f of x as x approaches c from the right-hand side. For the limit to exist, the left-hand limit must be the same as the right-hand limit. And if that is true, we no longer have to speak about the direction, and we can just say that the limit of f of x as x approaches c. Please note that the limit of f of x as x approaches c does not have to be the same as f of c, which we will see on the next page. We are given a piecewise function that is not continuous. We will discuss continuity later in the course. If we look at the limit of f of x as x approaches 1 from the left, we find it to be 1. The closer x gets to 1 on the left-hand side, the closer y gets to 1. Note that the curve does not go through the point 1, 1, but this does not affect the limit. The limit of f of x as x approaches 1 from the right is 2. Since the curve is constant to the right of x equals 1, the limit of f of x has to equal 2 as x approaches 1 from the right. Since the two limits, the left-hand limit and the right-hand limit, are not the same, the limit of f of x as x approaches 1 does not exist. Finally, f of 1 equals 2. The value of f of 1 equaling 2 has nothing to do with the actual limit of f of x as x approaches 1, as we will see in further examples. In this next example, again a piecewise function, we see that the limit of f of x as x approaches 1 from the left is -1. As we walk along the curve and approach x equals 1 from the left-hand side, the y value approaches -1, although it does not actually reach the point 1, -1, because of the open dot at the point 1, -1. The limit of f of x as x approaches 1 from the right is 1 for the same reason. As we walk along the curve and approach x equals 1 from the right-hand side, we approach the point 1, 1, but do not actually reach that point. However, the limit is still equal to 1. Therefore, since the left-hand limit and the right-hand limit are not the same, the limit of f of x as x approaches 1 does not exist. However, f of 1 is equal to 0 because there is a point at the point 1, 0, a closed dot. In this example, the piecewise function has a hole at the point 1, 1. The limit of f of x as x approaches 1 from the left is 1, and the limit of f of x as x approaches 1 from the right is 1. Therefore, the limit of f of x as x approaches 1 is also 1. However, f of 1 does not exist. This next example has the same graph as the previous one. However, the point 1, -2 is now a part of the graph. Note that the left-hand limit and the right-hand limit are still 1, and therefore the limit of f of x as x approaches 1 is 1. However, in this case, f of 1 equals -2. This is a good example where the limit of f of x as x approaches some number does not have to equal the value of f at that number. In this fifth example, note that the limit of f of x as x approaches 0 is equal to 1. This is because the left-hand limit is 1 and the right-hand limit is 1. Also note that f of 0 is also equal to 1. So all four answers are 1. This is the hallmark of continuous curves, which we will describe in a later chapter. Whenever there is a vertical asymptote in the graph of f of x at x equals c, it is always true that the limit of f of x as x approaches c does not exist. We can see this in the next two examples. This graph has a vertical asymptote at x equals 2, and therefore the limit of f of x as x approaches 2 does not exist. However, if we look at the left-hand limit, we can say that the limit of f of x as x approaches 2 from the left equals -infinity. That is a shorthand to say that this graph goes down forever. Its limit still does not exist, but saying that it equals -infinity gives a bit more information. Similarly, we can say that the limit of f of x as x approaches 2 from the right is equal to infinity to signify that the graph is going up forever. Again, the limit of f of x as x approaches 2 from the right does not exist, but saying that it's equal to infinity gives a bit more information. F of 2 does not exist because there is no value of f of x at x is equal to 2. In the seventh example, we again see a vertical asymptote, this time at x is equal to -2. However, in this case, we can say that the limit of f of x as x approaches -2 equals -infinity. This is because the limit of f of x as x approaches -2 from the left and the limit of f of x as x approaches -2 from the right are also equal to -infinity, as both curves are going down forever. So therefore, the limit of f of x as x approaches -2 is equal to -infinity. We can say that all of these limits also do not exist. However, saying that they equal -infinity gives a little bit more information. In this case, f of -2, though, is equal to 0 because of the closed dot at the point -2, 0. This again is a good example where the limit as x approaches some number does not necessarily equal the value of the function at that number. One final aspect of limits is to determine what happens to y as x gets infinitely far to the right, or what happens to y as x gets infinitely far to the left. We describe this in limit notation with the limit of f of x as x approaches infinity, or the limit of f of x as x approaches negative infinity. One behavior of the function is that the graph can go up forever. So in this example, we would say that the limit of f of x as x approaches negative infinity is infinity, and the limit of f of x as x approaches infinity is also equal to infinity. Going up forever is saying that the limit does not exist. However, saying that the limit is equal to infinity is the same thing as saying that it goes up forever and gives more information than saying that the limit does not exist. Similarly, the graph can go down forever. So in example 9, the limit of f of x as x approaches negative infinity equals infinity because the graph goes up forever to the left. But the limit of f of x as x approaches infinity equals negative infinity because the graph goes down forever to the right. Another behavior of the graph is that it can become asymptotic to a line. In this case, the limit is a value, and we would say that the limit of f of x as x approaches infinity is L. So in this case, the limit of f of x as x approaches negative infinity is equal to 4, while the limit of f of x as x approaches infinity is equal to negative 2. Another behavior of the graph is oscillation. In this case, the limit of f of x as x approaches negative infinity is equal to 1 because as we go further to the left, this graph goes up and down, but gets closer to 1. The same thing is true on the right side. The limit of f of x as x approaches infinity is equal to 0 because the further to the right you go, the graph oscillates up and down, but gets closer and closer to the x-axis. Another type of oscillation that a graph can do is shown in example 12. In this case, the limit of f of x as x approaches negative infinity does not exist. The graph does oscillate, but keeps oscillating between negative 4 and 4, never getting closer to a value. Therefore, the limit does not exist. However, the limit of f of x as x approaches infinity is equal to infinity. This is because the graph is oscillating, but also moving up. So it will eventually get higher than any value of y. Therefore, its limit is infinity.